Starting off, this is Bessie. Nicknamed her that early on. Cool things here, part of the conveyor system. We've got an 18-volt drill motor here. Actually, that's probably our 7th motor we tested and tried through. First few sets, planetary gears were bad. And then the other sets, there was actually a safety function on the inside, where if you didn't have its specific system, it would not work. Hooked up to that is our normally open relay here, which is also hooked into a sensor system here, a diffuse sensor. This is actually part of the system that, through the programming in the computer, is telling our motor to actually start running the conveyor belt. It's also our locator of the bulbs. The suction cup here actually goes down to pick. The nice thing here as well, with it being an active system, if a bulb, when it's in place, for some reason does not grab, and it'll still read it's there, it'll actually do a linear search down about 3 or 4 times to see if it can find a bulb. If it doesn't, it actually stops the whole program and realizing it's probably a broken bulb to get a human in there to take that away and get it going again. Other than that active compliance, the whole system all knows that when the bulb's out of here, it'll stay stopped until the bulb is put into its proper container, and then it'll kick the conveyor back on.
Okay, so this system has a couple of passive compliance devices as well as the belts themselves kind of act as passive compliance. We got the axial. When we go to pick it up, you can see that the plunger can come down. The plunger vacuum gripper actually has a little bit of axial compliance and the rotational also, but our belts themselves act quite a bit, mostly as our compliance. That way we can go ahead and grip and not worry that we're going to crush one of these bulbs when we're trying to get it. So you push it in, you can just set these bulbs in any which way as they go through our conveyor. Before we had these pieces of duct tape on here, the belts would spread apart, and before we had these guide pulleys, the belts would spread apart, the bulbs would seep down, and by the time it got to that end, we couldn't grab it because our position would be just all over the place, inconsistent. So these guides actually, as it's coming along, if it is sunken down a little bit, they'll push it up and get it back up to the right position so that it can be grabbed, as well as orientate it axially or rotationally. So passive compliance here, passive compliance there, everywhere. It's just this whole conveyor system is nothing but a passive compliance device. Cool. We got also, what else? There was one more thing I'm forgetting. Oh yeah, the strength of this material that we're building out. We've got the supports so that these belts don't walk, because we have to have them nicely supported on both sides. Otherwise, it's torquing over on it, and the belts will walk off, and we won't have anything working.
So over here we have the tester. Once we know that there's a bulb here, our robot comes down, picks it up, moves to a certain location, and moves to test. Here, this whole system right here is filled with passive compliance. Down at the very bottom, you can see that we didn't, for our last robot, actually both of our last robotic projects, and some here we have hard workspaces, but here there are no hard workspaces, and that actually works to our advantage. This just is on some pretty flexible duct tape, and that's because when we press down, we press so hard, and sometimes we have the angle of the base of the light bulb is different, and so we don't want a hard fixed rigid support down here because we could potentially snap a bulb off at the base. And then working on up, we have lateral compliance up here at the top, so if it'll guide it in at here. We have rotational compliance as well, and axial compliance. If anybody wants to come look and see inside, we have two side contacts, and they're both spring mounted. So when you come in, the bulb comes in, and it's not initially wide enough, but when it comes in, it spreads it out, and so you're ensured a contact, a secure contact every time. And on the bottom, you have axial compliance because the contact on the bottom is a spring, and it conducts obviously. And it'll press down, and we have it press down a certain amount. And then here at the top, it's all chamfered, so it's chamfered so that when you push it in, you're not going to press down too far, as in to break the bulb. And you're ensured a pretty good test every single time. That's all passive compliance. Our active compliance here is another diffuse sensor that we have wired in, and when we come in, we test it, make sure that it tests, and we get several tests actually, but when it's all done testing and knows what type of bulb it is, then if, say, for some reason it picks it up at an angle, and we've had some pretty bad angles, but it'll guide it in, but sometimes it'll break suction. So say it tests it perfectly, but it still breaks suction, and we can demonstrate this just by holding on to it and not letting it. It'll sense that it's still there, and it'll come down, re-pick it up, and it still knows what it is, and it'll position, it'll place it in the correct position. Other active compliance we have is what type. All of these, when we load it up, we can load it completely randomly. It tests it, and then based on our next system, which Daryl's going to get into, it knows what type of bulb it is. So.
I worked on the electronic side of this thing. The bulbs, obviously, there's some resistance in the filament in the bulb. The other problem you have with bulbs is if you put too much current through the bulb, it has a positive temperature coefficient, so it will actually change resistance as you're putting it. So the trick was to find a voltage that was not only safe to use, you don't want to have 110 in any of your fixtures on your line. That's just for a danger factor, a safety factor. So I developed a circuit using a quad comparator, an LM339, a National Semiconductor part. And if anyone knows what a comparator is, basically it's a differential open loop op-amp. So what it does is basically looks at the differential between two input signals and toggles the output accordingly. So what I did is I set up a resistive ladder which correlated to the resistance of the bulbs so that it would measure the resistance of the bulbs and trigger one of three outputs depending on what we're testing 3 types of bulbs today. And I put in a 4th output if we try to do something different there. But what it does is it triggers the bits on the inputs of our on the I/O system for the robot, and we can actually measure based on the resistance of the bulb what the wattage of the bulb is. That resistance will change with the wattage of the bulb. So we not only can determine whether it's open or shorted the bulb is, so we have those 2 conditions to tell whether the bulb is good or bad. We can also tell what size the bulb is and put it in the appropriate packaging.
Would an analog read, would an ohm meter not work in this case?
It will. We just couldn't figure out a way to read the ohm meter into the I/O system. I didn't want to build an A to B converter to do that. So it was simple. It's just a simple ladder comparator using a quad op-amp, or quad comparator, a National Semiconductor device. And so I built the PC board for that and put that together, and we wired it in. So, and again, we're running our voltage. We're running 5 volts across the bulb, so it kept the current low enough for not only safety factor, but it keeps the bulb from self-heating and affecting the resistance of the element while in the middle of the testing. Okay.
All right, the final procedure, once you've tested and know what kind of bulb it is, obviously we want to package it. And a long time ago we had it so it could package, it knew what the 3 types of bulbs were, but it could only package 3, and it would put it in the right one every single time, the right space. But we wanted to, beef it up a little bit. We want to package more than 3 bulbs. And right now we have the capability to package 12 randomly ordered, the 3, obviously we're constrained to the 3 types of bulbs, about 12 randomly spaced bulbs at a time. And these are not, there's no complex, there's no passive compliance here other than, we allow enough space that if it basically gets there and releases it, then it'll get there. The compliance there is it's all active compliance, it's all in the computer, the programming. We have basically nested if-else statements with several incrementing and de-incrementing variables, and basically their job is to let it know when we put a bulb, a 40, and it puts it here, we have it increments a variable, and it knows that this space here is full, and it will never put another bulb in this space, so therefore ensuring safety. Also, more safety factors. If we fill a box, it prints on the screen. Most of this stuff is printed on the screen to let you kind of know what's going on. It knows when a box is full. So if we had 5 40 watts coming through in a single process, well, it'll come over, and if it hasn't filled all the boxes yet, well, it'll come over, it'll test, say, a 40 watt, but it knows that this is full, and it'll deposit. We could have had a separate location, but we just wanted to ensure that the process was completed. So it prints a message telling us that the box is full. We're going to go ahead and deposit the extra bulb. There's nothing wrong with it, but it's going to deposit the extra one in the trash, and so we can keep continuing with the process. Also, every single box, when every single box is full, each box has its own special variable to itself, the box itself. And when the box is full, it increments that variable. When all 3 variables are set to 1, we have a if-else statement at the very end that it aborts the process and gives us it's not aborting because there's something wrong. It's just ending the process, letting us know that we need to change out the packages and reload the conveyor. So.
So, Dr. Richter, would you like to be our Vanna White and load our conveyor?
Yeah.
Why not?
Do everything to pick up bolts. Easy part's dropping them off. Put them in the right location. Just let go. Put them anywhere.
And obviously in manufacturing, we'd have another system that would actually be loading this for us.
But you can get pretty close.
All right. If this was a true manufacturing process, I think our ideal setup here would probably be
You can go
a
one
super
side,
strong, like high tension belt with holes chopped in it, so that you
and then
put a hole.
the extra ones when you get running, we'll just load the extra ones out.
Mountain bike inner tube is kind of flexible.
Just want to let you guys know there's one with an X on top. Obviously, you can see from the scratch marks on the inside it's broken, but we want to let you all know this is broken. It knows what to do with a broken bolt. So it'll test, retest several times, make sure it's not just testing bad, and then it'll deposit the broken one with a different message than the extra ones in the trash.
Put it somewhere toward the front.
Okay, sure.
Cool. That works. Load them all in.
We don't have enough space.
Okay.
We're gonna add the extra ones in.
Sure. All right. So we're gonna start. Ready? Here we go.